Every time you look at your own body, in the mirror, at your hands on a keyboard, at your reflection in a window, you are witnessing one of the most violent quantum phenomena in physics. The same phenomenon that kept the entire early universe trapped in total darkness for 380,000 years. You just don't know it yet. See, here's the thing nobody tells you. Your body should be invisible. Completely, perfectly transparent. You're made of atoms, and atoms are 99.9999% empty space. If you removed all the emptiness from every human on Earth, we'd fit inside a sugar cube. There's almost nothing there. Light should pass straight through you like you're made of glass. No, like you're made of nothing at all. But it doesn't. Your skin is totally opaque. And the reason why connects your flesh directly to the cosmic microwave background, to the moment the universe became transparent, to the deepest truth about what matter actually is. This bothers me. Let's find out why you're not a ghost. Now I know what you're thinking. This is simple. You learned this in school. Atoms have mass. They have protons, neutrons, electrons, real physical particles. When you pack enough atoms together, billions and billions of them in your skin, your muscles, your bones, you get solid matter. And solid matter blocks light, right? A brick wall is opaque. Air is transparent. Density equals opacity. The more stuff you have, the less light gets through. Makes perfect sense. It's logical. It's what any reasonable person would conclude. But stop right there. Let me show you what an atom actually looks like. And I mean actually, not the cartoon diagram you saw in ninth grade. If you took the nucleus of a hydrogen atom and scaled it up to the size of a marble, a little glass sphere you could hold between your thumb and finger, the electron orbiting, it would be a speck of dust circling at the edge of a football stadium. Not at the 50-yard line, not in the front row, at the outermost seats, hundreds of feet away. Everything between the marble and the speck? Nothing. Vacuum. Pure empty space. Now imagine your hand. Your hand contains approximately 10 trillion atoms, 10 to the 28th power. But if every single one of those atoms is 99.9999% empty space, then your hand is almost entirely nothing. It's a ghost pretending to be flesh. And yet when you hold it up to a window, not a single photon of sunlight makes it through. Not one. Your hand casts a perfect shadow, sharp-edged and dark. So what is light actually hitting? What's stopping it if there's basically nothing there? And why doesn't all that emptiness just let the light sail through like wind through a chain-link fence? We'll come back to this mystery. It's going to turn everything you think you know about matter upside down. Where are you watching from? Drop your location in the comments. And if you've ever looked at your hand and realized you have no idea what you're actually seeing, hit subscribe because this is about to get much stranger. Let's eliminate the obvious answers, because the obvious answers are where the real physics hides. Maybe you're thinking, sure, one atom is mostly empty, but when you pack 10 trillion atoms together, all that emptiness overlaps and fills in somehow. Like a forest. One tree doesn't block your view of the horizon, but a million trees side by side create a wall you can't see through. The gaps disappear when there are enough objects, right? Nice try. But no, here's why that doesn't work. Emptiness doesn't add up to fullness. You can stack infinite zeros and you still get zero. If I gave you 1,000 fishermen's nets and asked you to layer them perfectly on top of each other, you'd still have holes. Bigger nets, more layers, tighter weave, doesn't matter. The holes don't disappear just because you add more nets. They just create more spaces. The spaces between atoms don't magically fill in when you add more atoms. They remain empty. The math doesn't save you. Okay, different approach. Maybe it's the nucleus blocking the light. The nucleus is incredibly, almost incomprehensibly dense. A single teaspoon of nuclear material would weigh billions of tons on Earth. Protons and neutrons are packed into a space so small that all our intuitions about matter collapse. Maybe when light encounters this ultra-dense core, it bounces off like a ball hitting a wall. Hold that thought about density. We'll see why it's actually irrelevant in a moment. Wrong again. And here's why. Even in the densest matter in your body, even in your bones, nuclei are so microscopically small and so absurdly far apart relative to the wavelength of visible light that a photon should thread between them effortlessly. Imagine trying to hit a specific grain of sand with a thrown baseball while the sand grains are scattered randomly across an area the size of Texas. The odds of a collision are essentially zero. And that comparison is actually generous to the nucleus. In reality, the size ratio is even more extreme. Light waves should slip between atomic nuclei like you could walk between skyscrapers spaced miles apart. So if it's not the piled up emptiness, and it's not the dense nuclei, then what's left? The electrons? Now we're getting warmer. But stay with me, because this is where common sense dies and the real physics begins. Electrons are point particles, or maybe they're probability waves smeared out in space. Honestly, depending on how and when you measure them, they're both, or neither, or something we don't have proper language for yet. But here's what they're definitely not. Little solid balls with surfaces you can touch. They don't have edges. They don't have skin. In the classical sense of a thing you could hold, they're basically nothing. Mathematical abstractions that happen to carry charge and mass. So how does nothing block light? How does a probability cloud stop a photon? This question is going to lead us somewhere profound. But first, I need to tell you what light actually is. Because common sense is just a collection of prejudices we acquired by age 18, and your common sense about light is almost certainly wrong. Light is an electromagnetic wave. Not sort of. Not metaphorically. Not like a wave. Actually a wave. It's an oscillating electric field coupled to an oscillating magnetic field, the two dancing together, propagating through space at exactly 299,792,458 meters per second. And electrons? Electrons are electrically charged particles. They carry negative charge, and that charge responds to electromagnetic fields the way a leaf responds to wind. And here's the key that unlocks everything. When an electromagnetic wave, a photon, encounters a charged particle like an electron, the oscillating electric field of that wave exerts a force on the charge. It pushes it, pulls it, makes it accelerate, makes it jiggle. Now imagine a photon of sunlight approaching your skin. It's not approaching a surface like a ball approaching a wall. It's not hitting anything solid. It's entering a region of space absolutely swarming with electrons. The outer electrons in the atoms and molecules of your skin cells, trillions of them in a single square millimeter. The electric field of the photon starts shoving those electrons back and forth, making them oscillate at the same frequency as the light itself. Those jiggling atoms, and I mean specifically the electrons in those atoms jiggling, absorb the photon's energy. The photon ceases to exist as a propagating wave. But the electrons can't hold on to that energy for long. Quantum mechanics won't allow it. The energy is re-emitted almost immediately, typically within a billionth of a second, as new photons, but scattered in random directions. Some go backward, which is what we perceive as reflection. Some go sideways and get absorbed again by neighboring atoms. Almost none continue straight through in their original direction. Let me give you an analogy to make this physical. Remember how I said earlier that we discover why density doesn't matter? This is that moment. Imagine your skin is a dense forest, but instead of trees, the forest is packed with millions of tiny radio antennae, each one a few feet from its neighbors. Now you send a radio wave into that forest. What happens? Every single antenna starts vibrating in response to the electromagnetic wave. Each antenna absorbs some of the signal's energy and immediately rebroadcasts it in a chaotic spray of directions. The original clean wave gets shredded into electromagnetic noise. No coherent signal makes it through the forest intact, not because the forest is a solid wall, but because the electromagnetic interference is constant and relentless. That's your skin. That's what's happening every time light touches you. You're not a wall. You're a forest of antennae screaming back at the light. But I'm getting ahead of myself. Let me give you another way to picture this. Imagine you're a strong swimmer trying to cross a pool in a perfectly straight line. But the pool is completely filled with people, hundreds of them, and they're all thrashing, splashing, swimming in random directions. You dive in and start swimming. Immediately, someone's arm hits you, spins you sideways. You correct course. 2 seconds later, you're shoved backward by someone doing backstroke. You try again. Someone grabs your ankle. You're not hitting walls. You're not stuck. You're just being constantly, violently redirected by dynamic interactions with other moving bodies. You will never make it across that pool in a straight line. The pool is still mostly water, mostly empty space between the people, but the interactions are so frequent and chaotic that straight line travel becomes impossible. That's a photon trying to pass through your flesh, not blocked by stuff, redirected by forces. But here's the question that should be forming in your mind right now. And if it isn't, let me plant it for you. If this is purely about electrons interacting with electromagnetic waves, then why is glass transparent? Glass has atoms. Glass has electrons. Glass even has more atoms per cubic centimeter than your skin in some cases. What's the difference? Why can light pass through a window, but not through your hand? This puzzle will take us deeper into the quantum world, but the answer is going to blow your mind. Have you ever held a piece of glass up to your skin and wondered why one is invisible and the other isn't? Tell us in the comments. Here's the answer, and this is where the universe reveals how deeply strange it actually is. It all comes down to energy levels. Electrons and atoms can't just exist anywhere they want. They can only occupy specific quantized energy states. They're like people forced to stand on specific stairs in a staircase. You can be on step 3 or step 4, but never in between. The space between steps is forbidden. When a photon encounters an electron, the electron can only absorb that photon if the photon's energy exactly matches the energy gap between the electron's current level and an available higher level. If the photon's energy doesn't match any allowed quantum jump, the electron can't absorb it. Quantum mechanics says no. The photon just passes by, ignored like it was never there. In glass, the electron energy level spacing doesn't match the energy of visible light photons. Visible light has the wrong frequency, the wrong energy, so it passes through the material almost completely unabsorbed. It's like walking through a crowded room where every single person is deeply absorbed in their own conversation and completely uninterested in you. You're invisible to them. They don't even glance up. You walk straight through. In your skin, the molecules, proteins, lipids, melanin, all the organic complexity, have electron energy levels spaced perfectly to absorb visible light. Every photon gets grabbed, absorbed, re-emitted in a random direction. It's like walking into a room where everyone immediately stops what they're doing and surrounds you, asking questions, demanding attention.